Let's just get straight into it. So B11 was the most requested one. Um, and so in this question, what I'm giving you is a series of ionization energies for a single element. Right. And so we know that it's a row 3 element. Right. So that means that if we're, looking at the periodic table, right, it's going to be, one of these guys right here. Right. So sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Right, those are going to be our options in this scenario right here. So looking at it right here, right, I don't give you the first ionization energy, and the reason for that is that you can easily look up the first ionization energy, and I think there's even a different problem that gives the first ionization energy. So going through the steps of how to think about and how to approach this, right, you could have just easily skipped all of that, but you don't need to do that in this case right here, right? So I gave you the first 7 ionization energies, right? That's a lot of ionization energies, and looking through it, right, what we can see is the second one has an ionization energy of 2,252 kilojoules per mole. Third one is 3,357 kilojoules per mole. The fourth one is 4,556, right? And so each one of those, this is about 1,000 kilojoules per mole difference, right? Same thing for this one right here. So IE2, IE3, IE4, right? As you're going through all of those, you're having about 1,000 fold change. But then now here, when you're going to IE4 to IE5, right, what you're seeing is about 2,500 kilojoule difference between those two, right? So that tells us, right, just off the bat, just looking at those right there, that something happened. More than likely, it's a combination of either switching from taking out sulfur, or sorry, like p orbital or s orbital electrons, right, to whatever is next in that series, or we're switching from having now all of a sudden, either a fully filled set or a half filled set in those cases. So, right, so that's one big thing that we see there. The next thing, right, we see now go from IE5 to IE6, right? That's only now, a 1,500 kilojoule change. And then from IE6 to IE7, we're seeing, almost 20,000, right? About, I guess you could say like 19,000 kilojoules per mole, right? So that's a huge jump. Now, each one of those jumps should signify to us a few different things, right? So as I already had mentioned, the jump from IE4 to IE5 should tell us that that change is now going to be a change where it's going to be a change within the same row, right? Because it's a jump, you're increasing it from, changes in 1,000 kilojoules between the different ionization energies to suddenly 2,500 kilojoules per mole in those cases, right? So that's telling us then that what we're starting to do now is either breaking up fully filled or half filled orbitals, or we're switching from a P to an S, or P to a D, or something along those lines, right? Where you're still in the same row, but there's going to be then a change, right? Because now all of a sudden, again, you're going to be taking out fully filled orbitals in those cases, right? So those are the jumps that we're seeing there. And then, right, IE5 to IE6, the change between those two, right, is now less than 2,500. It's still higher than what it was before, right? But it's still less. So then that tells us, right, that we're probably still working within the same orbitals when we're taking out those electrons. But the big change, right, that IE6 to IE7 of like 19,000 is telling us that more than likely, we're switching rows in that case, right? Because now all of a sudden we're really taking a perfect octet or fully filled row, right? And we're starting taking electrons out of that. And that starts becoming, even more unfavorable in those cases, right? So those are the things to look at when thinking about these types of problems, is being like, what are the changes in ionization energies? And that should start telling you what's actually happening. And so, the going through, right, doing that, looking at all of those breaks is worthwhile. The next thing I would recommend doing is just simply starting to assign what the actual chemical process is for each one of those ionizations. So that way we can kind of get an idea of where we're at. So if we're doing that, right, so even though IE1 isn't listed, right, IE1 is going to be the transition of, element X to form X plus, and release one electron in that case, right? IE2 is now X plus, releasing an electron to form X2 plus an electron. IE3 is X2 plus to form X3 plus an electron. IE4 is X3 plus to form X4 plus and release an electron. IE5 is X4 plus going to forming X5 plus an electron, right? IE6 is X5 plus an XE5 plus forming X6 plus an electron, and then IE7 is X6 plus forming X7 plus an electron in this case, right? So we have the breakdown of what all of that is, and now the question is, right, how does all this stuff compare, right? So if this process right here, right, is switching a row, right, because that's the IE7 right there, right? So if that's switching a row because you're seeing that huge increase, then that means that essentially, right, the 6 plus is going to be, the configuration that you have that matches, lithium plus, or not lithium plus, right, sodium plus, in this case, right? It like 6 plus is going to be, a full octet, right? Noble gas configuration, right? That's what that 6 plus should be, right? Because if we have a full octet, right, we would expect that to take a lot of energy, in those cases, and then, removing one more electron from that, right, breaks that full octet and everything, which is where, the 27,000 would make the most sense. And so if we say that 6 plus is the full octet, right, we can then start working our way backwards, where, well, which element, right, would give us, an electronic configuration that matches neon, if it was in the 6 plus state, right? And so if that was the case, right, then we just have to simply add up, right? We go, 1, 2, 3, 4, 5, 6, right? So sulfur 6 plus has a neon electronic configuration in this case. And so because of that, right, we can then deduce, right, that this is going to be sulfur in this case. And that matches up too, right, with everything else that we're seeing, right? So if we're talking about sulfur, right, we have that first transition, that ionization energy that we don't, have listed here, so we can't really do any relationship with it. But we can see then, right, that the transition from, X plus to X2 plus, right, is reasonable. 2 plus to 3 plus, right? So this right here is then X plus, right, sulfur X plus. This is X2 plus. And then this is X3 plus in terms of electronic configurations, right? So you have X3 plus, right here. So those first three, right, those changes in ionization energy, they're pretty consistent. They're not dramatically different between them, and everything, right? There's no huge jump, which makes sense because all we're doing is simply plucking out electrons at that point from the p orbitals. And so then the fourth ionization energy, right, we're going from wait a second. Yeah, so right, so then so that's 3 plus, sorry. And so then, X4 plus has the calcium configuration, right, where you have now 3s2, right? So you have that 4 orbital. And so now, right, if we're taking the 3 plus, or sorry, the 4 plus sulfur species, right, and we're plucking an electron out of that, we're now breaking up a filled s orbital, right? So that way we would expect that to be more like have a larger change in energy, in ionization energy, which we see, right, when we do the jump from IE4 to IE5 in this scenario, right? That, beforehand we were only really changing by like 1,000 kilojoules per mole. Suddenly, right, we're jumping up to 2,500 kilojoules per mole, right? And that has to do with the fact that now, the IE5 is breaking up a filled orbital completely again, right? And it's breaking up the s orbital. And so we see that jump that matches what we have there. And so then we have the next, right, X5 plus is then going to be sodium in that case, right? And so removing that electron from X5 plus to form the X6 plus, which is the neon, right? That makes sense that doesn't take as much energy compared, like, in terms of the change in energy that we're seeing between IE5 and IE6, right? That it doesn't take that much energy because even though we're taking it out of the s orbital and stuff, right? What we're doing is now forming a fully filled octet in that case, right? So there's a certain amount of stability now that's being generated by simply being like, okay, well, might as well pull out that last electron and get a fully stable, noble gas configuration in that case, right? And so that's where the X6 plus is. But if we're then at X6 plus, and then we decide, okay, well, let's take one more electron out, we're already, pretty far away. But now, right, we want to go and make X7 plus in that case, right? That we would expect that to be a huge jump in that case, right? Because not only are we continuously taking electrons out of something that has a huge positive charge, we're also now breaking up, a noble gas configuration, right? We're taking, even more so from a filled octet in that case. So that's why we would expect it to be, an even bigger jump in that case. And so that's where, looking at the trends, looking at how does the change in ionization energy, right? How does that change, right? Because the ionization energy is always going to go up. The more positive charge you have, and this, goes to be, right, why do the successive ionization energies increase, right, is that you have to think about the fact that, an ion, right, so an element, an atom doesn't want to have a ridiculously high charge, right? It doesn't want to go to something that's 6 plus, right? Because, it's going to take a lot of energy because now you're going to have a huge imbalance in charge because you then now have to have at least 6 minus counter charges available, right, to interact with just that one balled up 6 plus ion in that case, right? And so that's not terribly, favorable. There are elements, right, that do it, right? So sulfur does form the 6 plus configuration. The thing is, right, that it has to then actually, be bound in those cases and distribute that positive charge. But that's why, right, the ionization energies are steadily increasing, is because essentially, right, the effective nuclear charge is increasing as well on all those different electrons because now there's less electrons around to kind of, interact with all of those positive charges, right? Because we're not losing protons, we're only losing electrons in these cases. And so, doing that and then, increasing charge, it, makes it less favorable to do. So you need more energy, right? You have more effective nuclear charge pulling on those electrons. That's happening. Not only that, right, you're also decreasing the radius, right, the ionic radius, because, as, you pull electrons out, right, everything kind of contracts. So everything as things contract, things start to, become more stabilized because they're closer to the nucleus, right? So you have that interaction, and so it becomes more and more difficult to pull those electrons out. But yeah, but that's how you approach 11, right? Is you have to look at the different ionization energies and figure out, well, where are we seeing breaks in, the changes in energy in each of those cases, and then being like, okay, right, like this makes the most sense to line up with, this type of change. Either it's going from, something that's half filled to now having less, or from something that is, going from a P to an S, or going from, a one row to the other row, in those cases. And so, those are the things to think about for those types of problems. So that's B11.